Hello and welcome. In this video, we will review the process of using the precise definition of a limit to prove a limit statement. So let's get started. Before reviewing a guideline for proving a limit statement, let's first review the precise definition of a limit by answering the following question. What is the precise definition of a limit? Well, this definition describes the behavior of a function near a point based on the behavior of its input. To help provide more details, let's consider the general statement for a limit. This expression says that the limit of the function f of x equals the real value L as the input x approaches the real value a. In other words, the function f of x approaches L as the input x approaches a. To visualize these behaviors, suppose we have the graph of the function f, with the value L on the y-axis of this graph, and the value a on the x-axis. Let's also consider a region containing L on the y-axis. To indicate the size of this region, let's use a positive value represented by the Greek letter epsilon. And let's require L to be the center of this region. This means we can use the letter epsilon as the distance from the letter L to the boundary of the region on both sides of L. Let's refer to this region as the epsilon region. And if we let f of x represent any value inside this region, then the absolute value of f of x minus L, which represents the distance between f and L, is less than epsilon. Going back to the statement for the limit, if this statement is true, then for any epsilon region, there exists another region centered around A, but not including A, where every point in this region is related to a value within the epsilon region. To indicate the size of this region, let's use another positive value, represented by the Greek letter delta. Since A is the center of this region, we can use delta as the distance from A to the boundary of this region on both sides of A. Let's refer to this region as the delta region. Now, if x represents a value in this region, this means the absolute value of x minus a, which represents the distance between x and a, is less than delta. Since this region does not include a, this absolute value is greater than 0. And so, in bringing all these ideas together, let's look at the formal definition, which says the following. For every positive value epsilon, there exists a positive value delta, such that if the absolute value of x minus a is greater than 0 and less than delta, meaning x is within the delta region, then the distance between f of x and L is less than epsilon, which means f of x is within the epsilon region. Now that we've reviewed the precise definition of a limit, let's now review a procedure to help prove a given limit statement. So let's look at a general guideline. In this guideline, we have the general statement for a limit. And for the proof, the first step is to let epsilon represent any positive value. The second step is to note that a delta value needs to be chosen such that the absolute value of x minus a is greater than 0 and less than delta. And we need to keep in mind the delta value chosen is determined in step 3. For the third step, the keywords "and so" are used to indicate the start of the proof based on the given inequality. The goal is to show that the absolute value of f minus L is less than epsilon. And this can be done by factoring and/or rewriting the expression. In addition, this step helps determine the chosen delta value. With this guideline in mind, let's look at an example. Consider the following limit statement. This statement says the limit for the function 2x plus 1 equals 7 as x approaches 3. So let's prove this statement. To begin, let epsilon represent any positive value, and we will need to choose a delta value such that the absolute value of x minus 3 is greater than 0 and less than delta. And so, based on this inequality, the absolute value of f of x minus L is equal to the absolute value of 2x plus 1 minus 7. This equals the abs value of 2x minus 6, which equals the abs value of 2 multiplied by x minus 3, which then equals 2 times the abs value of x minus 3. At this point, recall, the absolute value of x minus 3 is less than delta. This means our expression is less than 2 times delta. With this product in mind, consider the delta value equal to epsilon divided by 2. This means our product equals 2 times epsilon divided by 2, which equals epsilon. Hence, our chosen delta value needs to be epsilon divided by 2. This last result proves our limit statement. So let's practice this concept by proving the following limit statements. In the first statement, we have the limit of x squared plus 3 equals 4 as x approaches negative 1. Let's prove this statement. First, let epsilon represent a positive value, and we need to choose a delta value such that the absolute value of x minus negative 1 is greater than 0 and less than delta, which means that the absolute value of x plus 1 is greater than 0 and less than delta. And so, the absolute value of f of x minus L equals the abs value of x squared plus 3 minus 4. This equals the abs value of x squared minus 1. Factoring this expression, this equals the abs value of x minus 1 times x plus 1. And using a property of absolute values, this equals the abs value of x minus 1 times the abs value of x plus 1. At this point, recall, the absolute value of x plus 1 is less than delta. Yet, we do not have an inequality to describe the absolute value of x minus 1. And so, consider the following restriction. For delta less than or equal to 1, this means the absolute value of x plus 1 is less than 1. So, the abs value of x minus 1 is equal to the abs value of x plus 1 minus 2. With this expression in mind, recall, the absolute value of the sum is less than or equal to the sum of their absolute values. This means our expression is less than or equal to the absolute value of x plus 1 plus the absolute value of negative 2, which equals the abs value of x plus 1 plus 2, where the absolute value of x plus 1 is less than 1, which means our expression is less than 1 plus 2, which equals 3. Hence, the absolute value of x minus 1 is less than 3. Returning to our original product, we can now say that this product is less than 3 times the absolute value of x plus 1. And since the absolute value of x plus 1 is less than delta, then this product is less than 3 times delta. With this product in mind, consider the additional restriction. For delta less than or equal to epsilon divided by 3, our product is less than or equal to 3 times epsilon divided by 3, which equals epsilon. And so, the restriction for delta are delta needs to be less than or equal to 1, and delta needs to be less than or equal to epsilon over 3. Hence, the delta value that needs to be chosen is the minimum value between 1 and epsilon over 3. This last result helps prove the first limit statement. Let's now look at the second limit statement, which reads, the limit of 2 divided by x plus 3 equals 1/3 as x approaches 3. For the proof, again, let's begin by letting epsilon represent a positive value, and we need to choose a delta value such that the absolute value of x minus 3 is greater than 0 and less than delta. And so, the absolute value of f of x minus L equals the absolute value of 2 divided by x plus 3 minus 1/3. This equals the absolute value of 6 minus x minus 3 divided by the product 3 times x plus 3, which equals the abs value of negative x plus 3 divided by the product 3 times x plus 3, and this equals the abs value of x minus 3 divided by the product 3 times x plus 3. And this equals the product of the abs value of x minus 3 multiplied by 1 divided by the product 3 times the abs value of x plus 3. At this point, recall, the absolute value of x minus 3 is less than delta. Yet, we do not have an inequality to describe the second expression in this product. So consider the following restriction. For delta less than or equal to 1, this means the abs value of x minus 3 is less than 1. So, by definition, this means x minus 3 is greater than negative 1 and less than 1. Now, if we add 6 to each term, we get that x plus 3 is greater than 5 and less than 7. And using the reciprocal property for inequalities, this means 1 over x plus 3 is greater than 1/7 and less than 1/5. In turn, this means that 1 over x plus 3 is greater than negative 1/5 and less than 1/5. Since negative 1/5 is less than 1/7, and by definition, this means 1 over the absolute value of x plus 3 is less than 1/5. Multiplying both denominators by 3, we get 1 divided by the product 3 times the absolute value of x plus 3 is less than 1/15. Returning to our original product, we can now say that this product is less than the abs value of x minus 3 multiplied by 1/15. Again, recall that the absolute value of x minus 3 is less than delta. So our new product is less than delta times 1/15. At this point, let's consider an additional restriction. For delta less than or equal to 15 epsilon, our product is less than or equal to 15 epsilon multiplied by 1/15, which equals epsilon. Hence, in this proof, delta needs to be less than or equal to 1, and it needs to be less than or equal to 15 epsilon. Thus, the delta value that needs to be chosen is the minimum value between 1 and 15 epsilon. This last result proves the second limit statement. And this concludes our discussion on how to prove a limit statement using the precise definition of a limit.